Okay, everybody. Electrostatics. Like the name implies, yes. I will predict that this section is hard. Here's why I predict that. Okay, when we were in mechanics, okay, the study of forces and energy and momentum and all that stuff, all right? When we were in mechanics, we studied forces separately by itself, right?
Yeah.
And then we studied energy separately by itself, right?
Yeah.
Okay. In electrostatics, the thing is we're studying about things with electric charge
With forces.
as long as they're not moving. Okay? Just as long as they're not moving. This is all we're studying about them right now. But in this study, it involves forces and energy and two new topics, which you may have heard, well, you heard about last year. The two new topics are not only electric force and electric potential energy, but then we're going to add a new topic. We're going to have electric field.
Didn't we kind of touch that last year?
Yeah, and electric potential. All right. Well, okay, yeah. So here's another thing that's confusing about this. I mean, electric field obviously sounds a little different than electric force. But electric potential sounds a whole boatload like electric potential energy, right? But they're different, okay? So what makes this unit of study challenging is that it incorporates all these things all into one unit of study, okay? Now when you get to Physics C next year, we actually split this stuff out and add more things in it. We study them separate. But for some reason, in our books, in beginning physics, they lump all this stuff together. And it's not that it's that hard. What's challenging about it is just keeping the different concepts separate, okay? Because there are definitely differences between forces and energy. Okay, name me some differences between forces and energy.
One's a vector.
Yeah,
one's a
vector.
scalar.
Okay, this is a vector, and this is a scalar. So the math is different, right? Over here, you're going to have, these sorts of things to add up. Okay, you're going to have trig and geometry to deal with. With a scalar and energy, remember, yeah, it's just algebra. Plus, minus, multiply, divide, straightforward, right? No directionality associated with it. And remember, when we're talking about energy, what we're generally looking at is just the beginning state and the ending state, right? How they relate, okay? So we don't care about what goes on in between so much. Now, if there's work, then we do. But initial energy equals final energy if we have conservation of energy, right? So we have conservation over here. So your biggest challenge in this unit is not that it's that hard, because it's not. Your biggest challenge, though, is going to be keeping this concept separate, not only between vector and scalar, but also between the electric field and forces, and electric potential and electric potential energy. So you really have four different things. They're actually all related, and I'll show you how they all relate. But they all are a little different, right? And so there's going to be a lot of questions on the exam when that rolls around, whether it's my exam or the AP exam, where they're going to be just asking questions where they're not that hard, but they're to see if you know the difference and how to apply these differences to a problem, okay? So, we're going to begin by talking about electric forces, all right? We're going to start right here, and then we'll get to electric fields today, probably, okay? And then we'll talk about energy. I think electric forces are a little easier for most of you to take care of and to work with. It's not that bad, okay? All right. So let's start off with just some basics. Okay, let's go to the very, very beginning. Okay, what are things made of? What is everything made of?
Matter.
Made of matter. What's matter made of? Atom.
Solid gas.
Okay, and what are atoms made of?
Electrons, protons.
Okay, you got three basic constituents. Okay? Now, you can get down more detail, but we're going to just go to this level. That's all the biggest level we need, or the smallest level we need. We got protons, electrons, and neutrons. Neutrons. N-E-U? Trons. For some reason I have trouble spelling that. All right, protons, electrons, and neutrons. All right. Okay. Give me more details. What do you know about these?
Positive, negative, no charge.
Okay, so we got this thing called charge. Charge, positive, negative, and nothing.
Zero.
Yeah.
Almost
No
all-
charge or charge, which is the letter Q, is 0 for a neutron. Okay? Now if you go a little bit deeper,
Which was like nearly massless? Electrons?
okay, and then we'll talk about their mass real quick. As far as mass goes, what kind of mass are we talking about?
AMU.
Protons and neutrons are about the same. They're about 1 AMU, atomic mass unit. So approximately 1 AMU. Now in physics,
We don't like that one.
yeah, they write small u. So get used to that one. Don't ask me why, but in chemistry they write AMU, and in physics they write just U. All right, small u. So that's atomic mass unit. Oops, atomic.
What are you gonna write? Atomic?
I don't know what I was going to write, 2 T's or something. Atomic mass unit. Okay, and 1 atomic mass unit is what, 1.66? Somebody look it up in their constant sheet for me, please. And I may have it on here.
Oh, my conscious is in that other bag. I'll let you do that.
1.66, 1.67, something or other.
10 to the negative 27 kilograms.
10 to the negative 27th kilograms. Is it 1.66? Is that right?
It says 1.6, this is proton mass 1.67 times 10.
Okay, 1.67. Oh, that's proton mass. Okay, go to
Where, what else?
atomic mass unit. Does it show it on there somewhere?
No.
Here, unified atomic mass unit, 1.66, yeah.
Okay.
All right, so it is 1.66. The mass of a proton is actually 1.67 e to the negative 27th kilograms. Okay, that's its actual mass. It's almost 1 atomic mass unit. There's a slight difference, which we'll talk about when we get to modern physics, why that is. Why there's a mass deficit here. It's a little bit less. All right, what's our mass for our neutron? Because that is also approximately 1 atomic mass unit, but it's actually 1.6 what? Anybody got that?
Neutron?
Neutron mass, is that on there? It shows it as the same?
Yeah, 1.67, though it's slightly more, right?
Yes. It's actually a tad bit larger than that. But since we're only carrying 3 decimal places, it doesn't show up. But it's actually a little bit larger. And the reason that is, if you want to go down a little bit deeper, protons and neutrons are not a basic particle of matter. They are constructed from things that are smaller. Okay? The word atom, or atom, it actually means smallest indivisible unit. Yeah, so they came up with the idea of an atom, and so gold atoms were a certain size, and lead atoms were a different size, and hydrogen atoms were a different size, but they were all small as they would get, right? But then they found out that those things would break down into pieces, and they found out they broke down into these pieces, these 3. And then they found out that protons and neutrons break down into smaller pieces still. Electrons, as far as we know, are it. They don't break any smaller, as far as we know. Okay, they are what do you call it? a fundamental particle of matter. Okay, as far as we know. But protons and neutrons are actually made up of what we call quarks. Okay? Yeah, and there are, now they've discovered 6. They don't believe right now that there are any more than that. But there are 6 quarks. There's an up, and there's a down.
And there's 3 of each.
There is a, remember the other ones?
Positive.
There's a charm and strange.
And there's a left and a right.
And there is a top and a bottom. I don't know. I think maybe physicists stayed up too late at night, too much caffeine, or
Not enough.
something else. All right? Now, of all these different quarks, the matter that we have,
The bottom of the strange tar.
the ordinary matter that we see today, is made up of protons and neutrons and electrons. And protons and neutrons are made up of up and downs. Okay? Now the up quark has a charge. Okay, quark. Okay? The up quark has a charge of plus 2/3.
Are we going to have to use this?
No. Plus 2/3 of an electron. And a down has a minus 1/3 of an electron. Okay? So how do we make a proton? You got an up, and a down. And that makes a proton. Because I've got a plus 2/3 and a plus 2/3 and a minus 1/3, which gives me overall a plus 1 electron charge here.
Wait, so can the proton be made out of a charm and out of the top and out of the strange?
There are other things that could be made up of like 2 charms and 1 strange. I don't remember which one. I think the charm is positive and the strange is negative. I don't remember off the top of my head. I have to look it up. But you could, but it wouldn't be called a proton. It'd be something else. Okay? Different particle. Okay, so the proton's always made up of 2 ups and a down, which gives it a plus 1 electron charge, because you got a plus 2/3, and a minus 1/3. Now, if you're going to make a neutron, what will you make that out of? It's also made out of ups and downs. So you'd have 1 up
And 2 downs.
and 2 downs. And that would give you no charge at all, right? It would be neutral, right? Now, but a neutron is slightly heavier than a proton. So what does that tell you about ups and downs?
Downs are slightly bigger.
Yeah, downs are slightly heavier. So that since the down is slightly heavier than this up, then the neutron is just a tad bit heavier than a proton. Okay? And as far as we know right now,
No.
quarks are not made of anything smaller. But it's possible. All right? You think so? There's actually some studies that have shown that they might be, but right now they don't know. Okay, our study of the atom. What we care about in electrostatics and electricity and magnetism is all of the objects or parts of the atom that have charge. So, we want to know about this, we want to know about this, and this. We don't care. Okay? The neutron plays no part in the stuff that we're going to study. Alright? Because it has no charge. Now, this is a little bit different than gravity. Gravitational force affects all things with mass. There's no such thing as positive mass or negative mass. There's just mass, right? And the gravitational force always attracts in along the radius. The electrostatic force is going to be a tad bit more complicated. It not only attracts, but it also repels, because there are not just one type of charge, there's 2 types of charge. So depending how they pair up, you'll get attraction or repulsion. Okay, so it's a little bit more complicated. All right? All right. All right, now, let's go back to like a 1700s, early 1800s laboratory. Okay?
Ancient what?
Ancient laboratory, yes.
A brewing lab.
Yes.
Not that old.
They go
Great,
deeper.
great.
All right, now.
Great.
How did they first start discovering this stuff about electricity? All right, well, okay, they found out that if you had two different materials and you'd rub them together, that they would have a strange behavior. Okay? Like today, here's our materials that we use a lot, but back in the day they would use things like glass and rubber and silk and fur. Okay? Nowadays it's really easy to generate charge because you can just take like a balloon. Plastic materials are easy to charge up. Just take a plastic balloon and rub it on your cat.
Rub it on Mr. Balloon.
Yeah, don't rub it on my head, it won't work.
Non-existent.
Rub the
hair.
whale with
On a furry animal, like a student or a cat.
Like a Chris.
the rare.
Like a Chris.
Yeah, like Chris over there.
He only
Now,
has like what?
If you have a lot of hair product in your hair, it won't work nearly as well.
Christian.
You just wish you had the ball in mind.
If you have, that.
Well, if I untie it, it will. Other than that.
All right. So here's what they were able to do. They took these materials and they were able to rub them past each other. And what they found out is they would become what they call charged. Now back then they had ideas of what they would call this electric fluid. This fluid that would either flow into or out of the objects. And that's actually how Ben Franklin coined the terms positive and negative. What he did was he noticed that there was a lot of similarities between their ideas of this electric fluid about they would be a certain kind of charge if they had a lack of this fluid, and they would have a different kind of charge if they had an abundance of this fluid. And he related that to positive and negative numbers. Okay? The abundance or lack of. And so that's how we get these terms plus and minus for charge. They were invented by Ben Franklin. Now, we'll find out later that we kind of wish Ben had called them the opposite charge. It would have helped us out a little bit. But back then they had no idea anything about this idea of atoms. Okay? And so they had this idea of the fluid, right? So, anyway.
The blob.
Yes. So what they would find is you would take two objects, like you would have like rubber and silk, or glass and silk, and you would rub them past each other. And then what you would find is that the one of them could pick up small objects, like dust. Like you could hold it out in a dusty room. You ever do that? Where you look, there's light coming in through the window, and you can see all these little specks of dust flying around through the air. You could take a charged object and place it up in that dust cloud, and they would be attracted. Okay?
So we could clean up
That's
dust
it,
by
could
having a
be.
magnet.
That's exactly right. There's electrostatic air cleaners, and all they do is have a screen inside of them that they charge up, and they just blow the air in the room past them, and it collects all the dust.
So is that the joke they tell about the pledge, the electrostatic?
Yes, and so there's some things that you spray on a cloth, and it helps charge the cloth, and you can just wipe it across, and it collects on there because it builds up a charge. That's exactly right. Okay, so they could collect stuff, and what they found out is they could collect stuff with one or the other, and they could collect on both. Okay? However, what they found out is that they would take one of these and they would charge an object with it by touching it. They would find all kinds of different weird things, like if they had a small object suspended from a thread, and if they had one object that they would bring close and they would charge it, if they would touch, it would attract first, be attracted, come over and touch, and after it touched, it would swing away. Okay? And it would now repel. So it would attract first, touch, and then repel. They're like, what the heck's going on? So they'd take the other one, and they could do the same thing. But what was interesting is if they took this one, which we'll just call positive, using Ben Franklin's terminology, they found that the positive object would charge this, what they believed to be the same charge. It would transfer its electric fluid over. And then if you would take another one over here, if this was positive and put a negative object next to it, then it would attract. Okay? And what they found is when they would take these two objects and rub them past each other, one would be positive and one would be negative. One would have an excess of the fluid, and one would have a lack of the fluid.
Like there.
Okay? A lack thereof, positive or negative. All right? And so they went through a whole bunch of simple experiments, and with these simple experiments they could find out lots of stuff. For instance, there appeared to be two types of charge, which is why they came up with the idea of the gaining of something or the lack of something, right? Positive or negative. Okay? They would also find out that a lot of things were neutral, and if they were neutral, they would be attracted to both. They didn't know why, but they would be attracted to both. Opposites would attract, like would repel, but neutral would be attracted to both. Okay? They also found out the difference between conductors and insulators. Okay? Because, like, for instance, if you had this object here, and if you put a conductor in between here, that was a conductor. And then you took your positive object up close here, and you touched this thing. Then this one would pick up the charge, if this was a conductor in between. But what would happen if it was an insulator in between? Nothing. Okay? So some objects would allow the electric fluid to pass between, and some would not. Conductors and insulators. Okay? They also found out that the closer you brought charged objects together, the more powerful the force between them would be. And the farther away you got, then the less the force would be between them. Okay? So, most of the basic stuff that we know about electricity could easily be discovered from very primitive, what we would consider primitive, laboratory experiments and apparatus. Okay?
Prehistoric.
Yes. Nowadays,
We're smart.
since we know about what an atom is made of, all right? Since we know what an atom is made of, positive, according to Ben Franklin's sign convention, positive means an excess of protons. So positive equals more protons, and negative equals less protons. Okay? Now, it's unfortunate a little bit
It's really.
that he called that positive. Protons turned out to be positive because, according to that sign convention, then it's the flow of protons onto or off of an object that causes charge.
But we know it's
That's
a
right.
Yeah, but unfortunately for us, now that we know what an atom is like, since an atom is shaped like this, with positive in the center and the negative on the outside, it's the negatives that are moving on and off an object, right? So, when positive means really more electrons.
Or less electrons.
Thank you. Less
That's why it's
electrons.
confusing.
Sorry. Means less
One
electrons.
reaction of how-
And negative means more electrons. It's the negative charge that's moving around. Okay? The negative constituent of the atom that's moving around. At least in solids. Now in liquids or in gases, you can have positive charge moving because they're not physically in a structure that ions can move around. Okay?
Oh,
But-
solubility and all that.
Yeah, so like, yeah, if you put salt in a liquid and put charge across it, the ions can move either way. All right? All right, so that's where we're at. Now, the next thing you want to understand is that we don't really have a fluid moving back and forth. It's the movement of electrons. And electrons have charge.
Yes, they do.
Okay? Electron charge is 1e. 1e. What is 1e? Look it up.
6 times 10 to the negative whatever. Behind it.
You know it?
Yeah, I did know it just a second. 1.6 10 to the negative 19. I forgot the exponent.
Okay, 1.6e to the negative 19, or times 10 to the negative
As
19
well as physics.
coulombs. Yeah, so we got our term coulomb. Coulomb is our unit of charge,
Because they're cool. It's in their lungs.
named after General Coulomb, I believe. I think he was a general.
J.
Oh, I just forgot.
Okay. He was in the military, this scientist. And Coulomb, it's named after,
Okay, C or capital lowercase, right?
His name was
It's capital.
it's capital C. Small c is speed of light, so this is capital C.
Well, that's a big difference.
All right? Now, everybody, hey, when we say electron charge, we mean the absolute value, positive. Now, we know that electrons are negative, right?
Yes.
But when we say electron charge, we mean the positive value. Okay? So don't get confused by that. All right? Now, this is important. Remember we said you could rub two things past each other? So say you take your balloon and you rub it against your pet cat, Fluffy. Okay?
Shocking.
If Fluffy was uncharged and the balloon was uncharged to begin with, so they were neutral. What does neutral mean?
No charge.
Yeah, but what does neutral mean?
Protons.
Protons
No,
are
even no excess, no.
Yeah, that means that Fluffy,
Amounts of protons.
Fluffy's in equilibrium.
Fluffy has protons and neutrons. The number of these,
You mean electrons?
yeah,
I like your ring.
protons and electrons are equal, right? And if you take the balloon, the protons and electrons on the balloon, the number of those are equal. However, if you rub them past each other, charge will flow from one to the other. Okay, we'll talk about why in just a second. You rub them past each other. So apply friction. Rub, rub, rub. Take them apart. Now the balloon is charged. Let's say the balloon turns out to be negative.
The cat's positive.
The cat must be positive.
If you touch it, it'll look.
Because we have what's called conservation of charge.
Is there any way to know which will give and which will receive? How do you know?
Based off of substance control, they were not there.
All right, hang on just a second. Conservation of charge. If the balloon becomes negative, the cat will have become positive. This takes us all the way back to our 1700s laboratory, right? When they're rubbing two things past each other, one's positive, one's negative. So they apply different amounts of force or charge, different reactions to the charged object, right? Okay, so the question is how do we know which one's going to be positive, which one's going to be negative? All right? I refer you back to chemistry and this diagram. You know what that is, right?
The periodic.
That's the periodic table.
I'm just like, I didn't recognize it, not without you do it.
Section.
Here, I'll give you a hint. H.
And the block, yeah.
Didn't ring a bell.
Fill it all in, please.
No.
Alex solve for the puzzle.
Here you go. AU.
Yes.
There you go. I know gold's down there
You
somewhere.
forgot the whole
Bill's
bottom
not
part
that
of it.
far.
I know, you forgot to
Hey.
be radioactive.
That's why we
Oh, now I
couldn't
see
The
what
one
it
that
is.
made up.
Oh, that makes
Really?
All right.
Gold's a bit too low.
All right, now.
Too far over there.
Hey, wait a minute. What the heck is the difference between stuff over here and stuff over here?
Metals and non-metals.
To the left has a positive.
Conductors,
charge.
insulators.
Conductors, insulators,
In between.
metals, non-metals.
Cations, anions.
Okay, talk to me about the outer valence shell. Ah. Okay, out here you've got one electron out there all by itself,
Unstable.
less stable, right? And over here the shells are nearly filled. Okay, so energetically wise, these become more stable when they fill up the shells, right? And these are unstable. It's easy to break that outside electron off, right? So, if I put an object like this in contact with an object like this one's going to be an electron stealer. This is going to be an electron victim. Right? It'll lose its electron.
So what's fur made of?
All right, what's that?
So what's fur made of?
Well, that's a good question. I don't know. So, if what you're doing is you're taking two objects with a different affinity for the outside electron. You're placing them in contact. When you do that, just by placing them in contact, electrons jump from one to the other. Now, what does friction add? Friction adds a little bit extra energy to
Cause
help
that change.
to help the change occur. Okay? So the more friction you give them, the more will jump across. Does that make sense?
And so stuff in the middle won't be good at.
Yeah, so like the stuff in the middle won't be as good. Or actually, if you take like gold and rub them past each other, nothing happens. Because they have the same affinity for that outside electron, right? So nothing happens. All right. So you have to take two dissimilar objects. Now I don't know, like balloon and cat. I think, don't quote me. I don't know.
Wait.
But I do know if you take rubber and fur, which is one of the things they always used, fur would become positive and rubber would become negative. So I would guess that fur and balloon, the balloon would probably become negative. That's my guess. If you take glass and silk, glass becomes positive and silk becomes negative. Now there's a whole chart that you can look up in chemistry. It's called the triboelectric chart or something like that. I don't remember the name of it exactly. But it lists essentially the electronegativity of their attraction of the outside electron. Okay? And so you can look at there and you can see what the difference between the two is. So if you put them together, the ones that attract the electrons more will become negative, and the ones that attract the electrons less will become positive if you put them in contact. Okay?
Okay, so you said the ones that okay, this is unstable and stable, right?
Electron givers, electron takers.
Okay.
Okay? And it all has to do with an outside valence electron shell. All right? Okay. So, two things. Where does the charge come from? Outside shell. And we explained why some become positive, some become negative. We also need to remind everybody, conservation of charge. This is one of our big conservation laws. Okay? The charge doesn't just magically appear or magically disappear. The net charge before equals the net charge after. Okay?
This change.
And the last thing is charge is quantized. Because charge comes in units of this. So if you take a balloon and rub it on your pet cat Fluffy, the balloon and Fluffy will have equal but opposite charges, and it will be in a multiple of the electron charge. It has to be. Because you're not going to pull off half an electron or a quark, right? All right, so there you go.
Well, you definitely
With
want to
conservation
pull that
of charge.
off because you're not pulling stuff off the protons.
Right. Not at this energy level. Not at friction energy levels. Now you can get higher energy levels where you would eventually break the quark or break the protons and neutrons apart into quarks, but not in this field of study we're in. Okay? All right. So there are 3 ways to charge an object. All right? Way number 1 is friction. And we just talked about that. The picture for friction is this. You take 2 objects. They're both neutral to begin with. You apply friction or put them in contact, rub them past each other, and when you do that, what you end up with is that one will become positive, the other will become negative, but the charges will be equal. So you'll have a plus charge here and a minus charge here, and these 2 charges will be equal. All right? Now you see that a lot. Some of you may notice that in a dryer. You know, you take stuff out of the dryer, everything's all charged up.
If you don't put
Did you say
in
static?
Yeah, if you don't put in softener, right? Fabric softener is a coating that helps, well, yeah, it cuts down on the friction and conductivity. All right? So if you don't do that, just put different types of clothes in there, they'll come out charged. All
So
right?
if I put softener on the cat,
That's correct. So if you rub your cat with softener first, and then rub the balloon on the cat, you'll get much less charge. Okay?
Chris, you need some softener for your hair.
That's right. So yeah, if your hair is all staticky someday, not that I would know anything about that, then just take a softener sheet and just rub it on your hair.
Basically, take it with you at all times.
That's right. So you have a softener sheet. You smell like laundry. Well, matter of fact, I have a softener sheet.
Was that your secret?
Yeah. But it does have nasty side effects. All right, now, here's the other thing. Let's talk about this for a second. All right, hey, shh. So let's do this again. Let's say we have two objects. I don't care what they are. Two objects like this. We apply friction to the two. Okay, now remember, if they're neutral, this is our picture of neutral. Neutral means that they have the exact same number of protons and electrons, okay? If I apply friction to them, what moves?
Electrons.
So an electron would jump, say, from here to here. An electron, say, would jump from here to here. Let's leave it at that, okay? Now look what that does. If we eliminate all of our matched pairs, so all of our matched pairs go away, we end up with this, right? A -2 charge, electron charge, and a +2 electron charge, right? Now you can visualize that two ways. You could visualize it this way, that since they're both neutral, you could say that 2 electron charge moves over this way. So 2 electrons moves from here to here, right? And that will give us this. You could also say, instead, that 2 positive charges move this way. So everybody see that that will give you the same result.
But we know it's electrons.
Now, so here's the deal. Until we understood what an atom was made of, then there was no way for us to tell if it was positiveness moving this way or negativeness moving this way. Okay? Now, this gives us what we call conventional current. Now, we're not in circuits just yet, but this is what we call electron flow or current. This is what we call conventional current or proton flow. Okay, guess what? Since we didn't know anything about atoms, we use conventional current because that's how all our sign conventions were set up.
So that's how we
Thanks to our good friend Ben Franklin. All right? Now that's okay. At this level of the game, it makes no difference. All right? Now when we get into magnetism, we're going to show there's a way for us to discover which one it is. All right? And it's really kind of ingenious how they did it. It's really straightforward and simple. Because they didn't know which one it was. All right? And they found out that it's this, electron flow. So if you get into electronics, it'll be important probably for you to know that it's electron flow. If you're just in basic electricity and circuits, we don't care. We're going to talk about conventional current or proton flow, and we know that in reality it's electrons flowing the other way. Okay? But if you hear current or flow or conventional current, that's positive proton charge carriers. Okay? That's all right. Now, the other way that we can cause charge to flow, way number 2, is called contact.
Of course, that's kind of the same friction, it's just not actually...
Yeah, it's kind of the same as friction. Except in friction you start with everything neutral and you create charge from nothingness. Okay? You create separated charge from nothingness is what you're really doing. In contact, you start with an object that already has a charge. Now, everybody, when I write that, or the book writes this, what does that mean?
Positive.
The object is positively charged. What's the object like inside? What's its proton and electron nature like?
There are more protons than electrons.
Okay, I just want you to make sure that you don't say things like,
No electrons.
it's made up of protons only and no electrons. That would be some sort of really crazy nuclear reaction. Okay?
pretty awesome.
What we have here is I'm just showing the excess charge. This is just the extra protons we have, right?
That's net.
This is the net charge. Very good. So we have a positive net charge. Now, if you take that and touch it to another object, the other object will pick up the same charge. Or, I should say, they will share a charge. Okay? Now, if this was neutral to begin with, then this is going to pick up the same charge and be positive. All right? Now, the amount of charge it picks up depends on several things. Number one, is it a conductor or not? Okay? If it's a conductor, then a conductor, by definition, allows charge to flow really easily and quickly. If it's an insulator, insulators do not, in theory, allow charge to flow, or just allow it to flow with difficulty. Okay? So like an example would be here. Is this right here? This extension cord? Okay? Alright, inside of here is copper. Alright? If I plug this into the wall, then it will be connected, this metal here, will be connected through the metal of the building, through the lines that you see going across the Trinity bottoms here, all the way out to a power plant somewhere. That power plant may be 100 or so miles away. Okay, now, it's easier for the electricity or charge to flow through metal, a conductor, for 100 miles than it is for it to flow through, what is that? 1/8 of an inch of plastic? That's the difference between a conductor and an insulator. Okay? Can electricity flow through this plastic? Yes. But it's easier for it to flow through hundreds of miles of copper or metal than it is to flow through 1/8 of an inch of that plastic. Alright? So if you have a high enough voltage, which we'll talk about later, it could jump across that plastic, but it does so only with great difficulty. Okay? It takes very little voltage to make it flow. In fact, nearly any voltage at all will make it flow through a conductor. Alright? So there's our difference between conductors and insulators. So if you have a conductor, then the charge they'll share it completely. If you have an insulator, only this region where it touches, it's able to jump across. Alright? Touch. Alright, so they'll share charge. So this will come out to be positive. So afterwards, it'll look something like this. 1, 2, 3, 4, 5, 6, 7, 8.
What do we?
Now, notice the net charge is still the same. 8 plus 8 here, plus 8 here. But now it's shared between the two. Hey, anybody have a good guess? What if I started out with something right here that was plus 8, and I had a little bitty one right here that was neutral, and I touched them, or connected them with a wire? Would they both end up plus 4?
Yes.
No.
It would be the
Depends on what the
surface, or it would be the
size is.
volume, it would be proportional.
Yeah, it'd be proportional to whatever he said.
Turns out that this one will be positive, but it won't have 4. Because it's much easier for these to spread out here than it is over here, right?
They don't want
So there'll be a proportionality depending on the size of the object. Okay?
But you can't have half of one over there, can you?
And that's just it. You can't have half. Now, you can have a half of a coulomb, because a coulomb is a random measure, right? But you can't have half an electron. All right? You can't have half of an
So
electron.
probably like 7 and 1.
What about a miniature electron?
As far as we know, all electrons are identical.
We hope.
Every experiment we've ever run to find to see if there's differences between them. Because that's a good question. Are there differences between electrons? As far as we know, they're all identical.
Why would there be so many maybes?
Because that's
I
what
don't
science.
know, I don't even know.
Yeah, actually, that's a good question too. Why are there so many maybes in science? And the answer is because there's no
There's not enough
answer
smart
key.
people.
There's no answer key for science. It's discovery as you go along. And so
The world's just a
need,
big baby.
you need to open up the possibility that what you just discovered
It's
appears
wrong.
to be correct, but someone may come along with a better understanding at a later date. The nature of science.
You're alive.
Okay?
No, my life is a lie.
All right, now we talked about insulators and conductors. Piece of cake. Oh, other thing about insulators and conductors. Insulator. If I take a charged object, all charged up, and I touch an insulator right there, and I take a charged object, same one, and I touch a conductor, right there. By contact, this should become positive and this should become positive, right? There'll be a big difference afterwards. When the charge jumps off here onto this spot right here,
It'll be at that spot.
what'll it do?
Stay at that
It'll
spot.
stay. Or it will move very slowly or with great difficulty. But if I put this positive charge right here, okay, what do positives do to each other? They repel. And this is why by contact things jump to a new land. Because they're all smashed together here, and positives don't like each other, they repel. They find each other repulsive. And when they have room to move out, they do. And right here, since a conductor allows charge to move, they'll actually spread out. And a crazy thing is they'll actually spread out to the outside edge. And all of the charge will be on the outside surface. Remember that. It's called electromagnetic shielding, and we'll explain why that is a little later.
Want to just be that way they can get further away from each other. Really.
Well, yeah. It's because since they can move and they're repelled, they move out to the farthest reaches of the object, right? So from a practical standpoint, that's why they're on the outside edge. But there's also another reason too, and we'll talk about it when we get to an electric field.
Another reason that stops, like if it was like that from you putting one in the center from staying there.
Yeah, they won't stay at the center. They'll all spread out. All right. Now, before I can talk about the last way to charge an object, we need to talk about electric force and Coulomb's law. Okay? So let's back up real quick. And we've already talked about this in forces, but let's reiterate it again. Reiterate.
Reiterate.
Reintegrate.
Yay, something I understand.
You got all what?
It's a double.
All right, here we go. Coulomb's law. Now we've talked about this already in forces. Coulomb's law states that the electric force is always along the radius, either directly toward or directly away between the charges. And K is a constant. All right, look it up. What's our constant K? What is it?
They're looking it up for me. I told them to do it.
1.38 times 10 to the negative
1.38.
It's
9E9. Newton meters squared per Coulomb squared, or appropriately similar.
Oh yeah, 99. It's not Coulomb squared per meter squared? No, meter squared per... Oh, never mind. I'm hurting my brain.
All right, 99. Nice, easy one to remember. Unfortunately for us, by the way, this is called Coulomb's law constant, K. Unfortunately for us, it doesn't make much sense in physics B, but in physics C you'll understand why. It's also written this way, 1 over 4 pi epsilon naught. That equals K, so it's the same number, okay? Epsilon naught is a more basic fundamental constant, okay? And so it's written that way, and mathematically you'll figure out why in physics C it's written that way. Okay, because it's not always going to be K, but you'll always have an epsilon naught. Okay? All right, so in case you see it one way or the other, no big deal. Okay, Q is the charge, and the charge must be in coulombs, and R is radius, and it must be in meters. Okay? So now that I have told you that, We're going to solve a problem here real quick, just a minute, but let's go on to what's the third way to charge an object? It's called induction. Okay, you ready?
It's like through the air, do something.
Okay, here's induction, everybody. You need to write down this entire process, because the entire process, there's several steps, is called induction.
Have a waffle.
Okay, here we go. You ready?
Yes.
Step number one.
That's it.
Listen. Step number one. You have a charged object that you bring close to a neutral object. Bring close, but do not touch. That's step number one. Exactly. When you're a little kid. Do not touch it.
Why are little kids so...
What do you mean, little kids? Oh, I'm sorry.
What do you mean, kids?
Oh, wait! Oh, kids are great, but they are obnoxious sometimes. All right, bring close but do not touch. Okay, step number two. Step number two. You get what's called polarization. Because there are different types of polarization, you'll hear the word polarization or polarize in waves as well. So you might want to write charge polarization. You get charge polarization. Now what does that mean? Okay? So here's step number two. I'm going to write this one in brown. So what that does is, remember this neutral object is actually made up of both protons and electrons, right? So what happens is the electrons congregate over here and protons congregate over here.
Congregate.
Yeah, now let's clarify what that means. The object is entirely made up of protons and electrons and neutrons, right? Neutrons don't care about this process at all. Protons are repelled. I've got protons here, so the protons are repelled. And the electrons are attracted. Now let's look at what really happens. What really happens is I have protons and electrons all over this object. But what happens is the positiveness over here pulls the electrons over here. And when you eliminate all the matched pairs, it looks like this. Protons on one side, electrons on the other. So it appears that protons have been shoved far away and electrons have been drawn close. In reality, what happens is the electrons draw close, leaving the other side with an excess of protons. Does that make sense?
Yeah.
All right. Now, step number 3.
Take it. Take your brain back.
Provide a ground. Okay, or better yet, provide
A crown.
an escape route.
Why does this sound like intros?
Because it is.
It's all the same stuff. Ninja exit.
Route, R-O-U-T-E?
Yeah.
Yes.
There we go, that looks better. Okay, provide an escape route. Or as they say in Finding Nemo, escape. All right. This is the symbol for ground. What you've done is you provide a conducting path to some other place. Now, what does that do? Well, in our position right here, what do these protons want to do?
Escape.
Escape. Now, in reality, what happens? Electrons are drawn up, right?
Yeah.
But the protons run away. In reality, what happens is more electrons drive up here and cancel out the excess protons. Okay?
More electrons or more protons?
More electrons come up here in reality. Because if protons appear to be moving this way, in reality what you have is electrons moving the other way, right? Okay, now, if I take this and take it away, what happens?
It just stays negative.
No, then
It stays like that.
These will come back, right?
Attract these-
So how do I keep them from coming back?
you disconnect ground.
Yeah, step number 4. Disconnect the ground.
This is like a huge circle.
Okay, once you disconnect the ground, voila. Now this object is charged negative. Now you can take this away if you want. If you eliminate this now, this is going to stay negative. So this whole process is called induction. So induction is you bring your charged object close, you provide an escape route, and it drives the charge you don't want off the object, and then you disconnect your escape route, and now the object is the opposite sign charge of what you started with over here.
And you can take out the positive charge.
So let's say this is positive,
Because it's yellow.
and I want to charge E in positive. Which method do I use? Friction, contact, or induction?
Fire.
Contact. So I touch him. Voila, he's now positive. Okay?
No, didn't work.
It should have
I don't see it.
All right, now, let's say I have this positive and I want to charge something negative.
Get it close.
Okay, what I do is I get it close. I'm going to charge this negative. So I get it close. I provide an escape route.
To yourself.
Well, actually, that would work.
And
Maybe.
it goes back to
Actually, it would work. It would drive it off onto my hand. Provide an escape route, disconnect the escape route, and then take this away. And now, when this was positive, this becomes negative.
No, you just touch it.
Yeah, and if I touch it again, I discharge it right by contact.
It was something where we touched that ball and we stood on books.
Yes, we'll get that out.
Right now? Yay.
No. Mr. Carter's class is not in static electricity just yet, so we haven't gotten out all the toys yet for that.
That was fun.
I like the
Wait,
shocky
Mr.
thing.
Bruin,
When
Yeah.
you put your
could
hand.
you charge an object by touching the battery gap thing, whatever, on one side, and then like hold like little end at the bottom of it, like say a cell phone, where you would charge it? Would you be able to charge it?
Sure.
Alright, Mr. Gonzalez said that you'll
I
either
think-
have the wrong voltage or you'll have the wrong amps or.
Oh, you mean to charge it like charge it to charge the phone?
Yeah.
You mean like charge the battery?
Yeah.
No.
No. What if you get the battery and you touch the little metallic wire and then you.
I mean, okay.
No.
Can we try this on?
Too many things off.
You will need a really large.
You have a greater
positive.
Oh.
Too late. Attract all
In
negative.
theory, yes. In practicality, plug it into the wall. It's much easier.
Raise your TXU bill.
Yes, you see.
You don't need like a
What's
huge
that green thing that
positive to
charges?
attract all the negatives.
Oh yeah, you just place it on the next
The
charging.
power mat.
Something.
All right.
Piece of metal where you adapt it to your phone and stick it on there.
Hey, everybody.
Curiosity.
Now let's talk about this polarization real quick. I didn't bring any balloons today in. We'll bring them next time. But if you take a balloon, rub it on Fluffy, and the balloon becomes charged. Now I take that balloon and I stick it against the wall. It will attract to the wall.
And it'll stick up there for
Or I can put it on the ceiling and it'll stay stuck to the ceiling.
It'll stay up there for a real while.
Not
Yeah.
forever.
You probably get to stay up there since it's cold and the the heater's running,
That's
the
what we did
air
last
is pretty
year,
dry.
Mr. Carter.
It should stay up all class period.
I was the one that stood on top and put the balloon up there.
Nobody
Now,
gives a
everybody, shh, look, here's what happens. If you have this balloon, and the balloon is an insulator, right? So if I charge up this balloon, the balloon becomes negative and the charge will stay. And if I touch it to the wall's an insulator. But look what it does to the wall. Okay, the wall is neutral. The wall is not a conductor, right? So it won't suck all the charge off the balloon, right?
But it'll,
Why does it attract to the wall? Because the wall is neutral.
Induction.
Because
Yeah, it's temporary induction. Because what happens is the wall is made up of atoms. Atoms normally look kind of like this, right? With the negative stuff going around the outside, right? But when you bring it close, what happens is the atom will polarize. And the electron will spend more time over here, and it'll stretch it out a little bit. Oh, sorry, wrong way.
what to say?
Sorry, it'll go like this. And the negative electrons will spend more time over here. The electron shells will be warped just a bit. Okay, so what happens is you have a charge separation. And so then you get, why does that cause attraction?
Because they're opposite.
These attract, but these repel. So why does
There's
this?
a longer.
Because there's a
Or
Ah.
the R squared.
Because it's pizza.
Because the attraction force is greater than the repulsion force because of the difference in distance. Does that make sense? So that's why a neutral object, as long as it can be polarized, will be attracted to anything. Now I say because if it can be polarized, because if the object is a neutron, the neutron itself cannot be polarized. That's why neutrons, none of this happens to it. So it can't be
don't they have
polarized.
positive and negative charges, those
Yeah,
things?
but
They can't, though?
as far as I know, now that
You'd think on a very, very basic level they could.
maybe on a very basic level, but not that I know of. That doesn't mean anything, quite frankly.
And they're so small that the difference they can move would be so bad.
I don't know. All right. Yes.
Since you're bringing balloons, can we have a party?
Good idea. You gonna bring party favors and party food?
Yeah.
Yes. Friday, Friday.
Yeah, it's Christmas
on Friday. Not even like a full
It's not Christmas on Friday.
Hey, the now world. Not even like a full blown party. Just like food and chill for like the last 15 minutes before lunch.
Hey, can you have this?
I believe in education.
Hey, who said we did it?
We
And
can
they
eat
multitask.
While we're being educated.
Maybe. Well, I'm not opposed to eating free food.
Because we're Mexican in here, so we didn't realize that. We're all Mexican.
We are?
That means
That's so.
That's not nice.
I will grant you that in general that means very nice food. All right. Okay, here you go. Positive, negative. Oops. Positive, negative,
Positive.
negative. All right, here you go, everybody. Here's your assignment.
Positive.
1 meter. 2 meters. Write this down because I'm going to collect this.
Oh, on a separate sheet of paper?
3 microcoulombs.
Oh, on a separate sheet of paper.
3 microcoulombs. 1 microcoulomb. There you go. I want to know the force, the net force on this one, the yellow one. Okay? I want to know the direction, the magnitude and the direction of the force on the yellow chart.
Wasn't this on Quest like a long time ago?
What's that?
Yeah, it was.
What'd you say?
It was on our evening work.
Yeah, this is a review question because you did this already when we were in forces. Okay? Okay, 3 microcoulombs separated by 2 meters. 1 microcoulomb separated south of this one by 1 meter. Oh, by the way, 90-degree angle right here. Okay? So nice and simple. All right? I want to know the magnitude. Question number 1, what's the magnitude of the net force on this one? And then what's the direction of the force on this one? All right? There you go. There's your assignment. And don't forget Foxtrot Physics.
Oh, this is...